This is day 37 of 50 days of tutelage. In today's class, I'll be talking about sequences and series. What is a sequence? A sequence is simply an ordered list that follows a specific rule. And oftentimes, these rules that they follow, you don't necessarily have to do too much about them. Although what we're going to be doing in this class is how to actually properly study a sequence and to extract a lot of information from them. For instance, if I start with this set of numbers, if I start with 1, then I go to 2, 3, 4. Obviously, everybody that is following this video can tell me what the next set of numbers are going to be. You know, they will be 5, 6, 7. Also, if I go this way as well, if I go, let's say I have 2, then followed by 4, followed by 6, followed by 8. And if I ask you to go ahead and complete this thing, then you can say the next number is going to be 10, because now you can see that I'm increasing this thing by 2. So without telling you the rule, from the pattern, you can easily tell what next. And lastly, if I have something like this, 1, 3, 9, 27. Now, you will be able to see the pattern that is going on here. And that is basically what sequences are generally. Of course, there are some sequences that are always much more complicated. For instance, if I give you a sequence that goes in this manner, so let's say I have a sequence 1 over 3, then I have 2 over 9, then I have 3 over 27, and this sequence goes like this. So what you're going to notice is that the numerator is increasing by 1, but the denominator is actually being multiplied by 3. 3 times 3 is 9, 9 times 3 is 27. This is 1, 1 plus 1 is 2, 2 plus 1 is 3. So there are some sequences like this, and I'm not going to be talking too much about them in this place. The only thing I'm going to be teaching you about them is how to find their nth formula, because beyond that, you won't be needing that unless you are in higher institution. So back to what sequences are. Sequences are ordered lists that follow a specific rule. And so one of the things we know about sequences is that sequence can be finite and they can be infinite. So what do you mean by a finite sequence and what do you mean by infinite sequence? So if I go now from the set of, let's say, natural numbers, and I list 1, 2, 3, and I go like this, and I write 10 here. Now, this means that I have a particular last term that I want in this place. There is an ending to this sequence. It starts from 1 and it ends exactly at 10. But if I write something like this, 1, 2, 3, and I indicate this without putting any other number at the end, that implies that I want these numbers to continue. And from the pattern, you know that the next number is 4, 5, and after 5, there's always another one. By the time you get to a million, there's always a million and one. By the time you get to a trillion, there's always a trillion and one. By the time you get to whatever big number it is, there's always addition of 1. So this sequence keeps going. So sequences like this, we call them finite sequence. And sequences like this, we call them infinite sequence. So finite sequence, they are kind of always easier to work with, but when it comes to infinite sequence, they can be a little bit difficult to work with. So the two major sequences that I'm going to be talking about in terms of categorization and the behavior. So this one now, I've been able to group sequences into finite and infinite based on their behavior over a long time. So this one always has an ending. This one does not terminate. This one keeps going on. Now, I want to group them based on their behavior, based on the pattern that you observe. Now, specifically, I'm going to be grouping them as the arithmetic progression and the geometric progression. So let's deal with the arithmetic progression first. From the name arithmetic progression, in this case, what we're doing is that our sequence follows a pattern of addition or subtraction, although addition covers for subtraction as well. That is why, in terms of operation, addition and subtraction, they are actually regarded to as the same thing, while multiplication and division, they are regarded to as the same thing, but that's not the context of this class. So arithmetic progression is always such pattern that you can observe with addition. And so if I give you a sequence like this, I give you a sequence 2, 5, 8, 11. Now you notice that this particular sequence here, the next term is always determined by the addition of 3. So this is 2, 2 plus 3 is 5, 5 plus 3 is 8, and 8 plus 3 is 11. So in that situation, you have what we call an arithmetic progression. Another way you can also judge an arithmetic progression is that subtract previous terms, immediate previous terms from immediate latter term. So what I mean here is that subtract 2 from 5, subtract 5 from 8, and subtract 8 from 11. So what you notice is that they will always have a common value. They will always have a common value. 5 minus 2 is 3, 8 minus 5 is 3, 11 minus 8 is 3. And this common value is what is called their common difference. And we denote that with a D. This guy 2 here is denoted as the first term. This is the first term, and we denote that as A. Sometimes some people like to denote it as A1. That is not our problem in this case. So if you have this, you have the first term and you have the common difference, there's a whole lot you can actually determine in this situation. As you can see, this is not ending, so I can get as many terms as possible. If I ask you, what is going to be the next term in this case? You will definitely tell me that that is going to be 14. 11 plus 3 is 14. But if I ask you, this is term number 1, term number 2, term number 3, term number 4, term number 5. If I ask you, what will term number 10 be? You have to go 14 plus 3, 17, 17 plus 3, 20. You go, at least you get there. But imagine I ask you, what will be the 1000th term? You cannot continue to add 3 till you get to the 1000th term. So therefore, we come up with a particular formula, a formula that generally represents this. It represents the sequence itself. That is why we say a sequence is an order list that follow a specific rule. And so we always define sequences as a function that is mapping from set of natural numbers to the set of real numbers. So a real number sequence is a mapping that is mapping from the set of natural number to the set of real number. I've discussed function in the previous class. So if you missed that class, you can always check it out. So what that means is that every sequence always speaks from natural numbers. So natural numbers from 1, 2, 3. And so whenever this function, the rule that the sequence is given, it will always pick the domain from the set of natural numbers. And there will always be a representative. So our f of 1 in this case is 2. F of 2 is 5. F of 3 is 8. And f of 4 is 11. So how can we now get f of n? That is the question. That is for any n that belongs to, so for any n that belongs to the set of natural number, how can we always represent them using a particular rule? And so that is what we want to do now. So the first thing we notice is that, so let's say the term for any of these guys, let's say a random term n, we'll pick a random term n. And then for this first guy, so let's look at the pattern that each of them follow. So 2, let's try to extract 2 from everybody. So this is the same thing as 2 plus 0. This is the same thing as 2 plus 3. This is the same thing as 2 plus 6. And this is the same thing as 2 plus 9. So that implies that this is also going to be the same thing as 2 plus something. But what we notice here is that this 0, this is 0, this is 3, this is 6, this is 9. If you notice, this number is actually increasing by 3. From 0 to 3, 3 plus 3 is 6, 6 plus 3 is 9. So which implies that all the numbers that we have here, they are all multiple of 3. And so in the first case, you have 3. In this place, you have 0 here. So 0 multiplied by 3, that's just nothing. In this place, this is 3 multiplied by 1 actually. In this place, this is 3 multiplied by 2. In this case, this is 3 multiplied by 3. Now, so you can see the pattern. The first case, you have 3 multiplied by 0. So from 0 to 1 to 2 to 3. So 3 is the common difference, just like we've been able to establish here. So if 3 is the common difference, how do we get the number that we are multiplying with it? You can see that this 0 has a relationship with n. The 0 has a relationship with n. When we have 0 here, n is 1. When we have 1 here, n is 2. When we have 2 here, n is 3. When we have 3 here, n is 4. So that can tell you that if you know the n, you can always get this multiple here. So the multiple, that will be the common difference, 2 plus the common difference, multiplied by. So what you notice is that the number that is being multiplied with the common difference is always 1 less than the number itself. So therefore, if this is n, this number will have to be multiplied by n minus 1. And what is this? This is your first term. So let's write a common formula like that. So f of n is going to be a multiplied by n minus 1 times d. Sorry, a plus n minus 1 multiplied by d. And this is a general formula for the nth term of any arithmetic progression. Any arithmetic progression will always satisfy this formula. And so generally we call it the nth term. So most places you see it as Tn equals n minus 1 times d. So we can apply that for this particular term now. So first term, second term, third term, fourth term, fifth term I got 14. So let's see whether this will be true. So this is going to be T5. T5 is going to be A plus. So since n is 5 now, so that will be 5 minus 1 multiplied by d. This is 5. This is 5. And this is going to be a plus 5 minus 1 is 4d. So therefore, you have T5 equals, what is A? A is 2 plus 4 multiplied by 3. So that will be 2. 4 times 3 is 12, and that will be 14. So you can see that that is how we get our nth term. So generally, another thing you should also observe here is that if I ask you for T4, that would definitely be A plus 3d. If I ask you for T10, that should be A plus 9d. If I ask you for T80, that will be A plus 79d. So you just notice that the pattern that we observe here now for T5, so if I'm looking for the fifth term, it will just be 4d. Sixth term, it will be 5d, and all of that like that. And that is the general representation for arithmetic progression. So you should be able to represent any term with that formula. And that is arithmetic progression for you. However, arithmetic progression, the common difference can also be negative. It can be negative, it can be positive. It doesn't really matter. So I've been able to teach you how to identify an arithmetic progression. Just subtract immediate previous term from the latter term and do it for all the elements that are given. When you do that and you get the same result, you have a common difference. So therefore, that is an arithmetic progression. And that's basically what that is all about. But what is now, that is that about the sequence part. What about the series part of this thing? So the series part is actually very easy and straightforward. Series is the addition of all the terms of a sequence. Series is the addition of all the terms of a sequence. So all these numbers that I have here, 2, 5, 8, 11. So if I add all of the numbers together, then what I've produced is a series. So a series is actually a single value, and which is the what? Addition, sum of all the terms that belong to that particular series. So you are talking about sum of all the terms where n goes from 1, 2, and it goes on and on. Now, if an arithmetic progression is infinite, so if you have an infinite arithmetic progression, then the summation of all the term will always be infinite. That means that arithmetic progression that is infinite arithmetic progression, or a sequence that is arithmetic progression and it is infinite, does not converge. So they will never converge. They will never converge. They will never converge. But if they are finite, then we can be sure that they will come. In fact, any sequence that converges will always have a value of sum. That is, the sum will always converge as well. Any sequence that is finite will always converge. Any sequence that is finite, their sum will always converge. So now let's see, how can we find the sum of a given term? So general expression for the sum. So for instance, let me use that 2 5, 8, 11 that we had earlier. So if I want to get the sum of the first two terms down, so I want to get the sum of the first two terms, I can say this is the same thing as 2 plus 5 plus, 2 plus 5, and that's 7. If I want to get the sum of the first three terms, okay, let me even start from the sum of the one, or just one term, like that's 2. Then I go here, sum of the three terms, we have what? 2 plus 5 plus 8. And if I increase it to 4, that will be 2 plus 5 plus 8 plus 11. Now 2 plus 5 plus 8, that is 15. This is going to be 26. But you cannot always do this. What if you have a very large number of terms that you need to add? How are you going to go about that? This is why we have a general formula for the sum of any arithmetic progression. I don't want to bore you through the whole process of how we got this formula actually. So let me just give you directly. So to find the sum of any arithmetic progression, you have this: n divided by 2, then you have 2a plus n minus 1 times d. So, and this pattern can actually be properly observed if you actually play around this pattern and this set of addition very well. But I don't want to go through all of those things now. So we have n over 2 multiplied by 2a plus n minus 1d. So you can see where this, if it's an infinite series, it wouldn't converge, because by the time you multiply, if you're taking it to n equals infinity and you multiply everything here by infinity, everything is going to just be infinite like that, and it will never converge. So this is how to find the sum of an arithmetic progression. So all you have to do is, if I ask you to find the sum of, let's say, 8 terms in this situation now, that is, I want you to add everything from the first number, 2 plus 5 plus 8 plus 11, up to the 8th term. So all you need to do is just to substitute 8 into this place. So you have 8 divided by 2, then you know your a already. Your a is the first term, which is 2, so that's 2 times 2 plus n is 8, 8 minus 1 multiplied by 7, and that is going to be 4. So 2 times 2 is 4, plus 8 minus 1 is 9. 9 times 7 is 63. So 4 plus 63, that will be 4 times 63 plus 4, that's 67. So 4 times 67, let me quickly press that on my calculator. Oh, it is 8 minus 1 is 7. 7 times 7 is 49. Sorry about that. 7 times 7 is 49. So 49 plus 49 plus 4, that is 53. So 53. So it will be 4 times 53. 14, 4 times 53. Yeah, that's 212. So the sum of 8 terms in this arithmetic progression is going to be 212. So now we've been able to deal with sequence and series like that. Now, what if you know the last term itself? From the formula that I just gave now, I said S sum to the nth term is n over 2. Then you have 2a plus n minus 1d. But there's something that looks familiar there. So if you look at this now, what if I split the a, 2a rather, and I split it into a plus n minus 1 times d? You will observe that this particular guy represents something. It represents your Tn. So let's say the sum that you're looking for, you know the particular value of the last term. So this Tn can actually represent your last term. So therefore, Sn now becomes n over 2, then a plus. So this whole thing becomes the last term. So L is the last term in this case. That is, if you know the last term in that sequence, that is the value of your last term, then you can always use this as well. Okay, so let's go on. We have geometric progression now. Geometric progression. For geometric progression, this one deals with multiplication and division. Just like arithmetic deals with addition and subtraction, this one deals with multiplication and division, but we'll focus more on multiplication. So if you have, let's say, a sequence like this, so let's say we start with a 1, then we go to 2, then we go to 4, then we go to 8, we go to 16, and it goes on and on like that. For this one, if you try to do the test I gave you earlier, that is subtracting subsequent terms from each other, 2 minus 1 is 1, 4 minus 2 is 2. You don't even need to go further. It's already like 8 minus 4 is 4. It's already given like they are not the same. So therefore, this is not an arithmetic progression. But here's one thing you can do. You can divide them. 2 divided by 1 is 2. 4 divided by 2 is also 2. 8 divided by 4 is 2. 16 divided by 8 is also 2. So this is a geometric progression. That's how you test for geometric progression. So that thing that they have in common, that 2, 2, 2, 2, that all of them have in common, because we are doing a division, so we call it a common ratio. A common ratio, and we denote it with R. Of course, first term will still be A. In this situation, there's a general formula for this, and the general formula for the nth term of a geometric progression is A multiplied by R raised to power n minus 1. Actually, you can also observe the pattern just like I explained in arithmetic progression. If you list them out like that, you will actually tend to get it. So this general formula will always work for any geometric progression. So I've also shown you how to test for geometric progression. So just this. So if I ask you to look for, this is first time, second time, third time, fourth time, fifth time. If I ask you to look for the seventh time now, all you need to do is that your first time is 1, so that's 1 multiplied by, your R is 2, 2 raised to power 7 minus 1. So you have 1 multiplied by 2 raised to power 6, and that should be 64. That should be 64. So that's that about that. Now, we also have a way of knowing the sum of geometric progression. We also have a way of knowing the sum of a geometric progression. And for this one, even if it is infinite, it can still converge. But it depends on these things. So, but first of all, let's do generally what is the sum of geometric progression. So the sum of nth term of a geometric progression is given as A multiplied by R raised to power n minus 1, everything divided by R minus 1. I know some people like to say there's also another one, 1 raised to power R raised to power n, then you have 1 minus R. Actually, this does not really have any, it's not different from this. There's no condition. You can just stick with one of them and just use it. Because if I decide to factorize the negative sign here, for instance, if I decide to write this and I factorize the negative sign out, so this is going to be negative A multiplied by, so you now have minus 1 plus R raised to power n, and I factorize the negative sign here, so you have negative 1 plus R. So the negative sign will cancel out, and you still have R raised to power n minus 1 and R minus 1. So they are just the same thing. It doesn't really make any difference like that. So I'm going to stick with this one. So this is the sum, how to find the sum of a geometric progression. This is the general expression. And what if you now want to find, if it is an infinite sequence, how can you now find the sum? So I'm going to show you if it's an infinite sequence, how you can find the sum now. So one thing about this is that if you have a number, let's say a whole number or a natural number, or a number that is greater than 1, for any number that is greater than 1, so let's take R that is greater than 1. For any number that is greater than 1, if you take, for instance, now, a random number 2.4 is greater than 1. In fact, 1.06 is greater than 1. You can begin to raise this thing to very, very big powers. When you begin to raise this thing to very, very big powers, you notice that their values begin to grow exponentially. They are just becoming bigger and bigger and bigger. You can try it. For instance, you can try raising 1.06. You can raise it to power 100 if your calculator will be able to compute that. If you raise 1.06 to power 100, you have 339 point something. If you raise it to power of 1000, 1.06 raised to power of 1000, then it gives you a very, very exponential value. That implies that when you begin to raise this thing to a certain power, as the power becomes bigger, the number becomes bigger as well. But I want you to do the same thing for a number that is less than 1. Let us try 0.98. This number is less than 1. So if you raise this to a power, what you notice is that as their power grows, as their power increases, their value will be decreasing. So for instance, if you raise 0.98, let's raise it to power of 100. Let's see what that would be. By the time you're already getting 0.13 something. Now let's raise it to the power of 1000. I'm already getting something like 0.00000. So that implies that if I have values of r that are less than 1, at a point when I begin to raise them to the power, highest power, they begin to go closer to 0. So meaning that even though this is an infinite sequence, there is a particular point in time that I will get to that the value of my sequence every term will be tending towards 0. And so if you have such, that implies that the series will converge. So therefore, you can find the sum. So we now say we can find the sum to infinity. But under what condition? R must be less than 1. Although because R can also be negative, so we always choose the absolute value. So the only condition for a geometric progression to a geometric series to converge is for the absolute value of the common ratio to be less than 1. So if you want to find the sum to infinity of a geometric series, the first question you ask yourself is that my common ratio, is it greater than 1 or is it less than 1? If it is greater than 1, then it will not converge. So the value of that series will be infinity. But if it is less than 1, then it will converge. So let's look at it here. So this is going to be the same formula, a r raised to power n minus 1 divided by r minus 1. So well, from what I told you already, you observe that when you begin to raise this thing to very high power, if r is raised to infinity now, what will it tend to? Like I've explained here, r will tend to 0. So therefore, you now have this expression. So you have sum to infinity will be a multiplied by r raised to power n will now be 0. So 0 minus 1 divided by r minus 1. So sum to infinity will now be, so this will be negative 1. Negative 1 times a, that's negative a divided by r minus 1. If you decide to multiply both numerator and denominator by the negative sign so that you can let it disappear from the numerator, so you have a divided by negative 1 will now have positive sign and r will have negative sign. So a divided by 1 minus r. And this is how you find sum to infinity of a geometric series or of a geometric progression. And so that's basically all it is about arithmetic progression and geometric progression. But some sequences are actually funny, such that especially when you have fractions, when you have sequences given to you in fractions, you might want to take a little bit of pause and the nth time, and you want to determine the nth term of such sequence. So you might want to take a pause. For instance, if I give you a sequence like this, a sequence, let's say 2 over 3, then I have 5 over 6, then I have 8 over, let's make this one 12, then I have 11 over 24. So what you notice about this sequence is that you cannot actually pinpoint that it is arithmetic progression or geometric progression. But if you observe them separately, that is, you observe the numerator separately and you observe the denominator separately, you notice that this numerator is actually an arithmetic progression and it should have the pattern a plus n minus 1d. So the common difference here is 3. 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11. And the first term is 2, so you can have 2 plus n minus 1 multiplied by 3. So if you do that, this will be 2 plus 3n minus 3. And so that will be, what's 2 minus 3 is negative 1, so that will be 3n minus 1. So therefore, the numerator will be 3n minus 1 divided by, so look at this one now, it is a geometric progression. So using ar raised to power n minus 1, what is a? A is 3. What is r? R is 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24. So r is 2, so 2 raised to power n minus 1. So you can make this to be 3 multiplied by 2 raised to power n multiplied by 2 raised to power minus 1. So this is like 3 over 2 multiplied by 2 raised to power n. So you can say this is what? Divided by 3 over 2 multiplied by 2 raised to power n. So this will be the nth term of this particular sequence. Or you can just decide to say 3n minus 1 divided by 3 times 2 raised to power n minus 1. This wouldn't be bad as well. This is the nth term of this particular progression. So it is neither arithmetic nor what? Nor geometric. By the way, you will not be able to do the things that you we've been doing earlier, like sum and all of those nth term and the likes. You will not be able to do them here. There is a better way we actually observe series like this, but that is not for your consumption. And that will be the end of today's class. I'll see you tomorrow. Don't forget to like the video and subscribe to the channel as well.